I'm Mohammed Rostami. I'm a PhD student at UMass Amherst, and today I want to talk about our paper Redefining Passive in Backscattering with Commodity Devices. So backscatter communication, which is a form of passive communication, is becoming a popular choice for IoT applications. The reason is that backscatter communication delivers an extremely low amount of power consumption and in fact microwatts of power consumption. And this is good for IoT devices because they also want to consume very little amount of power so that they can work on a very small energy budget or even go beyond that and be battery free. And therefore, we have seen recently a lot of research work on how to enable practical backscatter communication, especially backscatter solutions that enable communication with commodity off-the-shelf radios such as Bluetooth and Wi-Fi, and therefore enable the vision of having a very low maintenance and deployment cost for IoT devices. However, in these proposed solutions, if you try to make them work in practice with a small energy budget, such as in battery-free packs, we face a huge energy gap that prevents from using such backscatter solution. Let's quickly describe what this gap is. But first, look at the commercial RFID links, which is a traditional system that use backscatter communication. In this system, there is a device called RFID reader, which is dedicated for backscatter communication. This device creates the main carrier signal, and the tag uses the harvest the energy from this main carrier signal into an energy storage capacitor. And when it reaches the enough amount of energy, it powers out and it starts, to modulate its data on top of this carrier by absorbing and reflecting this main carrier. And the resulting signal, which is called the backscatter signal, can also be decoded by this RFID reader. And in the presence of the carrier, in the presence of the main carrier, which is leaked from the transmitter to the receiver because the antennas are not perfectly isolated. This effect, which is called self-interference cancellation, however, can be overcome by using analog circuitry within the RFID reader, which is called the self-interference cancellation. However, in the proposed backscatter solution, we no longer want to use a dedicated RFID reader. Instead, we want to use a commodity off-the-shelf radio such as Bluetooth and Wi-Fi. However, this commodity radio, unlike a dedicated RFID reader, cannot transmit and receive at the same time. Therefore, we need at least two of these devices, one for transmitting the main carrier and the other one for receiving the backscatter signal. And here, we have the similar situation that the main carrier interferes with the backscatter signal. And here, because the commodity receiver is not anymore equipped with the self-interference cancellation, what these systems do is to introduce an internal oscillator into the hardware of the tag. And the signal produced by the oscillator is used to shift the frequency of the backscatter signal. So now the receiver can now listen to a different channel, which is not interfered by the main carrier anymore. However, there's a huge energy crisis introduced by this when using this internal oscillator. Even though the oscillators at the frequency of a few megahertz, can be extremely low powered in their steady state mode of operation. They need to actually wake up from deep sleep mode and pass a transient mode, which is basically called the warm-up phase of the oscillator. And during that warm-up period, even the most energy efficient oscillators use several microjoules of energy, which is orders of magnitude more than the amount of energy that can be stored by the tag in the tag when it tries to harvest energy in a reasonable amount of time. More specifically, the amount of energy that can be stored in the tag in a reasonable amount of time, let's say a few seconds, does not exceed the few nanojoules, which is 1,000 times less than the amount of energy required for simply powering up the oscillator. So the question that we ask in this paper is, how can we do the same frequency shifting of the backscatter signal, but instead of using an internal oscillator that faces this energy gap, instead of that, using passive elements, so the tag can afford, so that the frequency shifting is affordable by battery-free tag as well. So in order to address this question, we propose X-shift or external frequency shifting backscatter. So the idea at the highest level is simple. We take an envelope detector, which is a nonlinear device and is widely used as a receiver in this RFID and backscatter tag, and use it for a different purpose. The purpose is to take a twin carrier signal generated by another commodity device, and is basically two carriers with a slightly different frequencies, F1 and F1 plus delta F. And when this twin carrier passes through this nonlinear envelope detector, it will output a sine wave at frequency delta F, which can be potentially used to shift the frequency of the backscatter signal by delta F. So the same frequency shifting can be enabled, but with a passive nonlinear device instead of a local oscillator. Even though this idea seems promising and simple, we need to address a number of technical challenges so that we can make a tag, an actual tag with ultra low energy footprint, and also with a practical deployment consisting of commodity off-the-shelf radios only. The first challenge is, how can we generate a strong enough delta signal that can shift the backscatter, the frequency of the backscatter signal with passive elements. The second challenge is, how can we create the twin carrier signal with a standard commodity radio without touching its hardware, firmware, or introducing any modification to the standard whatsoever. And the third challenge is, how can we combat the intermodulation interference? To explain what that is, when the twin carrier signal is generated, it also goes into the receiver. And because of the nonlinear elements that exist in the receiver as well, it will form another version of delta F signal, which mixes with the main carrier and produces a signal at frequency F plus delta S, which is the same exact frequency as the backscatter signal F plus delta F. We call this effect the intermodulation interference, and we want to see how we can address this challenge. So for the first challenge, we see that if we try to directly connect the output of the envelope detector to a backscatter switch, it will simply fail, because the backscatter switch needs at least a few hundreds of millivolts to be driven successfully. whereas the output of the envelope detector has delta F with amplitude as low as a few millivolts. In order to resolve this issue, we use an ultra-low power circuit consisting of elements such as transformer and comparator, which are either completely passive or extremely low power. And since the delta F is in few megahertz or less, it can be extremely low power. Actually, in fact, our measurements show less than 10 microwatt, and more importantly, it does not need to consume any energy for warming up as opposed to oscillator, and that's the main advantage of our way of generating the delta. We call this whole block the delta generator block. For the second challenge, we see that among all the standard radios, the OSDM Wi-Fi signal consists of several subcarriers, which can potentially allow for generating a twin carrier by nullifying all the data subcarriers and keeping only two of them on. However, we realize that alongside the data subcarriers, which can be controlled by manipulating the data bits within the payload of the Wi-Fi packet, there are a number of other subcarriers called pilot tones that are always on, and in fact their amplitude and phase is determined by the standard and not by the data. And if you want to use the existing and legacy Wi-Fi standard, which use the entire Wi-Fi channel at 20 megahertz channel, the minimum number of pilot tones is 4. So it means that if we even nullify all the data subcarriers, the remaining signal has 4 carriers, whereas what we need is actually 2 carriers. However, there's an interesting thing about the newest standard of Wi-Fi called Wi-Fi 6 or 802.11ax, which introduces another mode of operation called uplink trigger mode. And in that mode of operation, we can only use a small fraction of the entire channel called a resource unit that can be as small as 2.2 megahertz. And when we choose to work with the smallest size of the resource unit, I mean 2.2 megahertz, it will only have 2 pilot tones. Therefore, if we nullify all the data subcarriers, what remains left is essentially a twin carrier signal with a pre-known amplitude and phase. And that's how we actually generate the twin carrier signal in action by using 802.11ax standard. So this shows the pipeline introduced in the 802.11ax standard for converting the data bits within the payload to the ultimate OSDM waveform. And we need to take this reverse direction from the desired waveform where all the data subcarriers are nullified and it only consists of 2 pilot tones all the way back to the actual data bits that will result in such waveform. And now for the third challenge, in order to overcome the intermodulation interference, what we do is to use a fraction of delta F for frequency shifting instead of the delta F itself. And the way to do it is to first dividing delta F by 2 using simple logic elements. Here we use D flip-flops for this purpose. And then using the third harmonic of the backscatter signal, which stands at frequency F plus 1.5 delta F. So the reason for not using F plus 0.5 delta F, which is the first harmonic of the backscatter signal, is that even though it's 10 dB stronger than the third harmonic, it is very close to the main carrier signal that is highly self-masked by the main carrier, and that's the reason for choosing the third harmonic. So we put together all these building blocks together with backscatter modulator, small microcontroller, the charge pump circuit, and the typical envelope detector as a receiver, and try to implement the full prototype of the tag with the off-the-shelf component. And the table shows that the power consumption of both the transmitter and the receiver are only a few tens of microwatts, which is in par with other proposed state-of-the-art backscatter tags. And we believe that if we convert this off-the-shelf implementation to an ASIC design, the power consumption can be reduced by an order of magnitude. But the main advantage of X-shift tag is that it does not need to consume any energy for the warm-up of the oscillator, which allows it to operate on the energy stored in the capacitor during the energy harvesting. So it allows for battery-free tag. And among all the various deployments that are possible with our tags, we choose to work with this deployment, where there's a Wi-Fi router consisting of two Wi-Fi cards, one for sending the twin carrier signal embedded into the Wi-Fi packet, and the other one is used for sending the main carrier signal, which is in the form of a Bluetooth low energy signal, but at a different frequency. So when the tag shifts the frequency of this main carrier signal, which is called BLE meter, the resulting backscatter signal would be exactly at the first advertising channel of the Bluetooth low energy system. And therefore, it can be decoded by a standard Bluetooth low energy receiver, such as the one in the cell phone. And here's a summary of the evaluations that we did on our system. It shows that in different line of sight and non-line of sight scenarios, you can achieve a few kbps of throughput at up to 2 meters of distance to the Wi-Fi router. Even though this throughput is relatively low, given that other proposed backscatter systems with CommodityDevices can achieve several hundreds of kbps or even megabits per second of throughput, this low throughput in X-shift is not because of the way that the frequency shifting is done, but it's because of the fact that our current implementation is based on the packet level decoding, which means that the data bits are translated to the presence and absence of an entire BLE packet. And in the future, when we convert this to a bit level decoding, the throughput can also be maximized to hundreds of kbps. And also about the range, we believe that by better impedance matching between the antenna and the nonlinear element, and also using the first harmonic and finding another way for overcoming the self-interference, we can boost the range to by several times as well. And we invite the prospective audience to read the evaluation section of our paper for further analysis on the energy benefits of X-shift, as well as a better validation for our design choice.